We continue to explore SymPy as we look at how to solve equations and systems of equations with SymPy. Okay, so solving equations and systems of equations with SymPy. Again, you remember that SymPy is a Python library for symbolic mathematics. So it can solve algebraic equations, it can solve systems of equations, it can perform symbolic calculus, it can manipulate expressions, work with matrices, and solve differential equations. Unlike numerical libraries, SymPy keeps mathematical expressions exact whenever possible. So sometimes you just want that exactness, not just some numerical approximation. And that is where SymPy becomes very helpful. And one of the first things you do when you use SymPy is you install it if you are using it for the first time. Once you have it installed, anytime you open the session, you then need to import it. So importation is like summoning it for work. So before solving equations, symbolic variables must be defined. So you have to define the variables you want to use so that in case you have several variables, you'll be able to distinguish which ones are your variables and all of that. So import SymPy as SP. That's where we import, and then we have a variable here which is X. This is when you are declaring a single variable. You use capital S symbol, that not plural. So you have X right there. Then you can also have multiple symbols. So you can declare as many symbols as possible at once. And like in this case where you have X, comma, Y, comma, Z, and then you have SP dot symbols, X, Y, X space, Y space, Z. Now, if you look at the two of them, you'll discover that when you declare one symbol, that one is capital S for symbol and it's not plural. The other one is small s but plural because you're declaring more than one symbol at the same time. So we run this also. It doesn't output anything because we've not told it to do that. So, and then of course, if you want it to come out, you can then maybe just type X like this and it just gets produced straight up. Now you see the other when you use print X, it's not as beautiful as when you just type X directly. So if you want a beautiful output, you just type the X directly. So see what this X looks like. It's not as beautiful as when you have just X like this. And it's that interest. Yeah, it looks more beautiful, like LaTeX produced. Then for X, Y, Z, also you could just come and say X, comma, Y, comma, Z, and then it comes out that beautifully also. Okay, it comes out as a collection. Then let's go ahead, since we're talking about solving equations. So let's start with linear equations, which are the simplest of equations, right? So imagine you need to solve 2x plus 5 equals 15. So of course, here, you subtract 5 from both sides. That will give you 2x equals 10. Then you divide both sides by 2, and you get x to be 5. So again, the symbol here is x. So imagine if it was not x, let's say if it was even p. So you have 2p plus 5 and you want to solve for p. So in this case now, you have to declare the symbol as p. So this is p, then the symbol is actually p. Well, you can use the plural one for even one symbol because it's the most convenient. You don't have to worry about maybe it is in capital letter or not. Then you now declare your equation. Equation is SP. So EQ is a function from the SymPy library, and then you have 2p now. 2p plus 5 comma 15. So you have the left hand side here, you have the right hand side here separated by comma, and then the solution is sp.solve. So solve is the keyword to solve the equation you have declared here, and you're solving in terms of p, not x anymore. So if you run that, it gets 5 as expected. So that is to solve linear equations. Then we come here and we want to solve quadratic equations. So let's say here now you don't want to use x. X is very common, but you can use any other thing. So q squared plus 5q plus 6 equals 0. That's what you want to solve. So definitely the symbol you're declaring should be q, and then that's q here. Everywhere you have x, you have to make it q. So you have q star star 2 plus 5 star q, and then you solve the equation with respect to q. So, of course, when you factorize this, you get q minus 2 into q minus 3. If you equate to 0, you get q is 2 and q is 3. So, and that's exactly what we have right here. Then, solving cubic equations too. Let's imagine that instead of calling it s squared, you want to call this r. So, this r cubed plus 6r squared plus 11r minus 6. So, here, what you have to declare is r. So, you have r, sp dot symbols, r So like I said, you can use the plural one here to avoid thinking about capital or not. Just use symbols and then you're good. Okay, it's R. Don't forget R. Then you have another R here, minus 6. So solutions, sp.solve equation with respect to R. So if you factorize this, normally it's going to be x minus, R minus 1 into R minus 2 into R minus 3. If you equate to 0, and you get 1, 2, 3, just like what you have right here. Now, before I go again, let me imagine that you want to solve I want to try to do something. Okay, let's say you want to solve an equation. You declare m as a variable. So m equals sp dot symbol. Since okay, in fact, let's say m n equals sp symbols. Okay. Yeah, it has given us all these options. But what I want to do here is this. I have m and n, right? So we now have, say, sometimes when you have some expressions, say, um, okay, let me take this m raised by 3 minus n raised by 3. Let's say plus 7 plus 7 divided by 3. Okay. And then you now want to solve this expression with respect to m. You want to make m the subject. So you see, it contains both m and n, but you want to get it in terms of m. So if you run that now, it gives you this plenty expression because you are solving a cubic expression. So it gives you all these things now in terms of n. So in case you have some expressions like that, let's make it like power 2 so the solutions don't get this plenty. Okay, well, let's make only m power 2. So in this case, you have maybe just two sets of solutions. So you have these two here now. So more like a quadratic expression solution now. So that's one thing you have if you solve that equation. Yeah. So how about talking about exact symbolic solutions? So SymPy returns exact symbolic answers whenever possible. Example, if you have x squared equals 2, if you solve x squared equals 2, that'll be plus or minus square root of 2. So, and of course, you can get it in numerical form or in the exact form, which preserves it. So if you have it as roots 2, it gets preserved. So your symbol is x. So you have sp dot symbols x solutions, sp dot solve x squared minus 2, uh, solve it in terms of x, and then you print your solution. So it gives you this minus square root 2 and square root 2. That's plus or minus root 2. That's exact. But then you can have decimal approximations of the same thing. And in that case, just like we've seen in previous videos, symbolic results can be converted into decimals using evalve. That is, you evaluate the function. So the solutions you have here now, so just say s.evalve for s in solution. So these solutions now, there are two of them. So the first one is negative square root of 2. The other one is positive square root of 2. So it runs over these two and gives you the approximate values. So if you run this now, you get minus 1.4142, blah, 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 and then 1.4142, and the rest of that. So you can get it in preserved form, in the exact form. You can also get it in decimal approximations as the need may be. Now, the next thing we want to look at, we've us already seen this using EQ. EQ, open and close brackets. So EQ, left side, right side, creates mathematical equations explicitly, with the left hand side being the left hand side of the equation and the right hand side being the right hand side of the equation. Like when you have x plus 4 equals 10, so left hand side is x plus 4, right hand side is equal to 10. So again, you can create your symbols. It doesn't have to be X, it can be anything, like I've been saying. So let me make this one Y this time around. So Y SP symbols, then we create Y and then equation now. So this is how you declare the equation. The EQ function is coming from the SymPy library. So you're solving Y plus 4 equals 10. So on the left hand side you have Y plus 4, on the right hand side you have 10, and they are separated by commas. So the solution now is sp.solve. Then you solve this equation now with respect to Y, because I've changed it. So you run that and you get 6. Of course, Y plus 4 equals 10. Subtract 4 from both sides. You have Y equals 10 minus 4, which is 6. So you use EQ to create mathematical equations explicitly. Then how about you want to solve rational equations? So rational equations, of course, the word rational talks about ratio. So a rational equation will be an equation involving a numerator and denominator equal to something else, like x plus 1 over x minus 2 equals 3. So to solve this normally, right, you multiply both sides by x minus 2, so that'll be x plus 1 equals 3 times x minus 2. That will be x plus 1 equals 3x minus 6. Then you can collect like terms now. So 3x minus 6. So you can bring x here. That's 3x minus x, which is 2x. Then the minus 6 can go to add to 1. So 1 plus 7. So you have 7 equals 3. 7 equals 2x. So that means x is 7 over 2. And that's exactly what we have here. So you create x equals sp plus symbols key x, and then equation sp dot equation, then you have the rational expression here, x plus 1 all over x minus 2. So you put brackets to make sure everything is neat, and then the right hand side is 3 because you're using eq. Then the solution is sp to solve the equation with respect to x. And just like I've explained this now, the answer is 7 over 2 when you run that, right? So that's solving rational equations. Now, how about solving radical equations? So to solve radical equations here, right? Of course, normally what you should do is, because of the square root, you square both sides. So if you square this side, you get x plus 4. If you square this side, you get x minus 2 squared. So that means you have x minus 2 squared will be x squared minus 4x plus 4. And then you collect like terms and you solve, and your answer should be like 5. So you're probably going to get two answers, maybe minus 5 and 5, I suspect. But minus 5 cannot work here because minus 5 plus 1 will be negative. So square root of negative will be undefined. So the only time it can be defined is when you have 5. Now, this is exactly what I mean. Root x plus 4 equals x minus 2. Okay, root x plus 4. So you have root square root of x plus 4 equals x minus 2. So you want to remove the square root, right? So you have root x plus 4. So you square that to remove the square root, then x minus 2 all squared. So power cancels root. So you have x plus 4 equals x squared minus 4x plus 4. So you can subtract 4 from both sides. So this goes away. And then you have 0 equals x squared minus 4x minus 4x plus x, right? Or better, minus x. Yeah. So you then have 0 equals x squared minus 5x. So that means that you have x into x minus 5 equals 0. So x is equal to 0 or x is equal to 5. Okay. So x can be 0 and x can also be 5. But in this case, when x is 0, right? Yeah, x can be 0 or 5 normally. So if you look at this now, 0 plus 4, the answer is 4. Square root of 4 is 4. So square root of 4 is 4. I mean, square root of 4 is 2. So 0 minus 2, that doesn't work. So 0 doesn't work here. It doesn't match the right answer, but 5 works. 5, you have 5 plus 4, 9. Square root of 5 is 9. I mean, square root of 9 is 3. Then 5 minus 2 is also 3. So that's why the correct answer will be 5 here. And 0 is excluded because it doesn't work. This what if it works for the right hand side, you have square root of 4, which is 2. 0 uh 0 minus 2 is minus 2. So that doesn't really work like that. So solving trigonometric equations now. So you can also talk about trigonometric equations. Like if you plot sine x, right? Sine x, they're always so everywhere it cuts the x-axis, you have the solution there, and you discover that happens around 0 and pi because it's 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 periodic with period pi. That's 180 degrees. So sine x equals 0 now. So you have x equals sp dot symbols x. So solution sp sine x. Of course, sine x comes from SymPy, and you're solving that with respect to x. So and the solution is 0, comma pi I. So sine x is 0 at whenever x is 0 or whenever x is 80 degrees. I mean 180 degrees or pi radian. So we talk about general trigonometric solutions now. So you want to solve. So here now you have a solve set which provides infinite solution sets when appropriate. So you have x is sp dot symbols x. So the solution sp dot solve set. So instead of just solve that you've been using, so sp dot solve set sp dot sine x comma x. So it gives you the solution, infinite solution set when appropriate. So in this case, you have 2 n pi, given that n is an integer, or an union 2 n pi plus pi, given that n is also an integer. So so you have this collection like this as a solution in that case. So as far as you have n as an integer, these are the possibilities right there. Then you then have you solving exponential equations. So okay, I want to do this kind of thing for cosine, you know. So let's do it for cosine and see what happens. So we use the solve set for cosine. So in this case, now we just have cosine. That's cos x. Now we're solving for x too. So it also, so you see the set it gives us 2n pi plus pi over 2, and then 2n pi plus 3 pi over 2, like that. So for cosine. So this is a very neat way to get these things out. So solving exponential equations, now we can also solve the exponential equations. You have 2 raised by x equals 8. Of course, 8 is 2 raised by 3. So if you equate the powers, x is equal to 3. So that's why we have this here. So you create the symbol, you get the equation 2x, 2 raised by x is 8. Then solution, you solve the sp.solve, and then you have 3 as your answer, and that's clearly true. Then solving logarithmic equations now. Log x is 2. So to solve logarithmic equations, you have to take the exponent of both sides. If you are using a natural logarithm, so that will be exponent of log 2 equals e raised power 2. If you are using common logarithm, that's log to base 10. So you take, so it means x is going to be 10 raised power 2. But obviously, this is log x here. We take it as natural logarithm or the Napierian logarithm. That's ln. So and that's why the answer is exponent of 2 in this case. So of course you declare a symbol, you have the equation. Of course, logs comes from SP and EQ comes from SP. Then you solve, which is a function also from SymPy that is, and you solve with respect to x, you get the exponent of 2. Then how about solving inequalities? Solving inequalities. I think there was a video I did on solving inequalities. I'm not, yeah, on that, I think that's under polynomial functions, yeah. Under polynomial functions, I talked about inequalities at some point. So you want to check that out if you're interested. So declare the symbol as usual. The inequality is x raised power 2 minus 4 greater than 0. So the solution then is, yeah, so you see the key function you use here is solve underscore univariate underscore inequality, which you get from the SymPy library. And then you take your inequality. So you solve that inequality with respect to x. And the solution is such that you have minus infinity less than x intersection x less than minus 2, and all of that union 2 less than x intersection x less than infinity. So you have the solutions in ranges like that. So so you have solution between minus infinity and minus 2, as well as between 2 and 2, between x line between 2 and infinity, like that. That's how you get the solution to x squared minus 4 greater than 0. So if you want to get more of the theoretical understanding, you can check my playlist on polynomial equations. So solving systems of equations, now you have x plus y equals 5 and 2x minus y equals 1. All right. So of course, this one we can, without even touching, we can add the two equations and we get 3x equals 6 because y will be eliminated. That means x is equal to 2, and clearly so. And once you know x to be 2, so you can put 2 here. So y is equal to 5 minus 2, 3. So of course, this is easy to understand. What if it is something more complicated? So you have to set that up that like that. So you have x, y equals sp dot symbols x comma y, x space y, then set up the first equation. X plus y is 5, 2x minus y is 1. Then the solution, you solve equation 1, equation 2, use for x and y. So you have that. Now, another thing we can do is we can have symbolic situations. What I mean by that is this. Imagine that we have, imagine that we have all these expressions now. Let me now add ABC. So instead of, in addition to AXY, so I have ABC. XY. So of course I have A, B, C, X, Y, like that. And then this one is now, instead of 5 here, I have A. Instead of 2 here, I have B. Instead of 1 here, I have C, like that. So, but then we still want to solve everything with respect to X and Y. So if you do that now, you get your answers in terms of A, B, and C. So X will be A plus C over B plus 1. Y will be A times B minus C all over B plus 1. So that's the kind of thing you can have it. So, and that's why this symbolic thing is really cool, right? I want to try something. I'm trying to say, if what if can I do AB solution 0 and it gives just one part of it? Okay, that's not working. Okay, I was thinking I could get something. Maybe I can get just one part of the equation. Okay, what if I do solution X? I'm just trying to do something where, aha, Yeah, this is what I was aiming for. So with this now, it brings it out very cool. So what if I do solution X and solution Y? Okay. Does it work that way? Okay, so solution Y comes later. So I can separate this. Yeah, I mean, this comes out more neatly than, if you had it the other way. So of course, okay, we can do the solution. We have this way, right? So it's like that long thing, but you want it neater. So you just do solution X, and you get A plus C over B plus 1, and then we can do solution Y. So when you separate them like that, the answers are neater than when you have it all modeled up. So you have AB minus C all over B plus 1. Then solving systems with three variables. So for you to solve this kind of thing, you can use elimination. You can also use matrices, right? You set them up as a matrix, and then you do the different. You can use Cramer's rule or inverse method and all of that. But that may be more tedious than you just using SymPy here. So just declare the variables x, y, z, sp dot symbols x, y, z. Then equation 1, x plus y plus z, comma 6. Equation 2, x minus y plus z, comma 2. Then 2x plus y minus z, comma 3. And then you solve equation 1, equation 2, equation 3 with respect to x, y, z. So if you run that, you have 5 over 3, 2, and 7 over 3. Then you have to solve solving nonlinear systems now. Like you have x squared plus y squared equals 25 and x minus y equals 1. Of course, normal thing that you should do here is you can make x the subject. So x is equal to y plus 1. So you substitute wherever you find x, you have y plus 1 squared plus y squared. So from there you get two values for y, and then whatever two values you get, to put them here, you now get two values for x. But that's a lot compared to SymPy. So for SymPy, just set it up, define your symbols, then define equation 1, x squared plus y squared equals 25, equation 2, x minus y equals 1, then solution, equation 1, equation 2, solve for x and y, and then you get minus 3 minus 4 for x. So for the first one, you have when x is minus 3, y is minus 4, or when x is 4, y is 3. So those are the solutions you get in that situation, solving nonlinear systems. How about solving systems using matrices? So like I described the other time, so for some kind of equations, you need to set them up as matrices. Like this one, you can set it up as matrices now. You just get the coefficients. So this will be 1, 1, 1, 1 minus 1, 1, 2, 1 minus 1, and then you have 6, 2, 3. Maybe I'll do it for that one later. So coming here now, you have 2, 1, 1, 1 minus 1, and then you have 7. So it's more like you have 2x plus y equals 7, and then x minus y equals 1. And then you set up the matrix like this. A is SP matrix 2, 1, 1 minus 1, and then you then have B, which is the right-hand side, the solution side. And if you solve that, you get 8 over 3, 5 over 3. So I'm just going to copy this now and do it for that system we did the other time. So I bring it back over here now. So what do we have for that? 1, 1, 1 is 6. 1 minus 1, 1 is 2. Okay. 1, 1, 1, 1, 1, 1. And this is 6 here. 1 minus 1, 1 is 2 down here. That's 1 minus 1, 1 is 2. Then you have 2, 1 minus 1 is 3. 2, 1 minus 1 is 3. So I can just copy this. 2 minus 1, 1 is 3. 2 minus 1, 1. And then I can copy this, and that is 3. 2 minus 1, 1 is 3. So with this now, we can just solve, and we get 1, 2, 3. And that was the answer. 1, 2, 3? Seriously? Here we got 5 over 3. Okay, I think there's something else I've not done here. A dot L is solve. Why should it be 1, 2, 3? Let me see. If you multiply 3 by 3, there's something is not right here. 1, 1, 1 is 6. 1, 1, 1 is 6. 1 minus 1, 1 is 2. Then 2, 1 minus 1. Okay, I think something is wrong with that. 2, 1 minus 1. Yeah, it's 2, 1 minus 1. Yeah, I think that's where the issue is. And then the right-hand side is 6, 2, 3. Yeah, I got the issue now. 2 minus 1, 1. Yeah, with this now, everything is fine. 5 over 3, 2, 7 over 3. 5 over 3, 2, 7 over 3. So when you have that, you can set it up like that, and you get your 5 over 3 to 7 over 3. So you can see that minus shifting here, change the whole thing. Okay, so with that in place now, Okay, this should actually come after the first one I did it. Yeah, okay, fine. That's also okay. I can leave it there. So this was the one we looked at before, so it's good. Then how about solving numerical solving with nsolve? So we can do numerical solving with nsolve. Some equations cannot be solved symbolically. So there are some equations that cannot be solved symbolically because you cannot separate the variable you're looking for. For instance, you have cos x minus x equals 0. Try hard as you may, you can't solve this symbolically. So you can do numerical solving using, we've been using solve for the explicit solutions we've been getting. But in this case, since you can't get the x apart, you use nsolve. So x is sp dot symbols x. So solution sp dot nsolve. So you now have sp dot cos x minus x. And you are doing that at 0.5. So you're evaluating that at 0.5 or so. So the solution then is 0.7390. So if you try to solve this way, okay, then of course, solving this, you may need to use things like there are many methods you can use, like a very good one would be the Newton-Raphson method, which converges to the solution faster. But of course, there are other slow ones like bisection, secant, and all of those. Right, but Newton-Raphson can be pretty good. All you just need to do is just say f of x equals cos x minus x. Then you now set it up like um, you know, uh, f xn plus xn minus the derivative over the original thing or something like that. So you can check numerical methods, numerical analysis playlist where I discussed all of these things. So this one you can solve these equations that cannot be done symbolically. Then solving differential equations now. You have dy dx equals that. We already know the answer here is c1 e raised power x. I think I did this in a previous video under this SymPy. So set up your symbols. So here now, when you solve a differential equation, their solution is going to be in terms of it's going to be y of x. It's going to be function y. So here you define x as symbol and define y as function. Okay, so the equation now becomes sp dot equation uh y of x diff x, that's like dy dx, comma y of x. So we are solving in terms of y of x. So solution now sp dot dsolve. So you use dsolve for solving differential equations of that equation, and the solution is neatly like this: y of x equals c1 e raised power x. That's what we get right here. Then, so we have some important SymPy solvers now. So you use solve for general symbolic solving. You use solve set for set-based solving, like when you're solving trigonometric equations. You use lin solve for linear systems. You use non-lin solve for non-linear systems. You use nsolve for numerical solving. You use dsolve for differential equations, and of course, solve underscore univariate underscore inequality when you're dealing with inequalities. So these are some of the things we've encountered. So let's talk about simplifying expressions, which we've also talked about previously in other videos, right? X is sp dot symbols x expression x squared minus 1 all over x minus 1. So sp dot simplify the expression, you get x plus 1. That's clear because x squared minus 1 is x minus 1, x plus 1. X minus 1 cancels, so you have x plus 1 left like that. Then you have substitution. So values can be substituted into symbolic expression using subs. So x equals sp dot symbols of x. So the expression is x squared plus 3x plus 2. So if you substitute 15 for x, 15 squared is 225. 3 times x is 45. So 225 plus 45 is like 260. Two no, yeah, 225, right? Plus 45. That is 270 plus 2, that's 272. So you can substitute. So you have your expression, and you then have the expression that subs. Then for x, you substitute 15 and you get this. So imagine if you make it 10, no, that'll be 10 squared, that's 100, plus 30, 130. So everything's going to be 132 if x is 10, like that. So you can substitute that way. Then you can expand expressions. So imagine you have x is sp dot symbols x, and the expression is x plus 2 raised to power 3. So sp dot expand expression, it gives you x cubed. Now I've discovered if you use print, it doesn't come, it comes out like s star star 3 plus 6 star x star star 2 plus 2 star x plus 18. So if you use print, it won't come out this neatly. So it's better you don't use print. Just allow it to come out directly. So you have x plus 2 raised to power 3 gives you x cubed plus 6x squared plus 12x plus 8. I mean, you can actually do it doesn't have to be this kind of power thing. It could be you putting together various functions, I mean various expressions. Like maybe let's do something in terms of t, for instance. So the symbol is t, and then you have x t plus 2 star t plus 2 star t minus 1 star t plus 4. You can continue as much as you want. Star t minus 2. So all this now, you just want it expanded. So you get t raised to power 4 plus t3 cube minus 8t squared minus 12t plus 16. So you can keep going. So let's now say t, let me say t plus 1, and then t minus 4 times t minus 4. So if you do that now, it goes like it's still power 4 here. Okay, so you have t raised to power 4 plus 3t cubed, blah, blah, blah. Now, what I've done is you have t plus 2, t minus 2. That's like t squared minus 4. Then t minus 1, t plus 1. That's t squared minus 1. Then you have t plus 4, t minus 4. You have t squared minus 16 or something. So if you put all of that together, this is what exactly you get right here. So how about factoring expressions? So you have sp dot symbols x, expression is x squared minus 5x plus 6. So if you factor that, of course, it's clear that that's x minus 3, x minus 2. Okay, so let's try to do the one we just did up there now. Let's take it back and see if we can get back our expressions. So you have t raised to power 4. So let's say this is t now. You have t here, and that symbol's t. So you have t raised to power 4. You have t raised to power 4. Then 3t raised to power 3. So plus 3 star t raised to power 3. Then we have minus 7t squared minus 7, 7 star t raised to power 2. Then we have minus 15t as minus 15t. Then lastly, plus 12. So plus 12. Let's factor and see if it gets us all that. But we need to factor the expression, right? That's something I'm not doing right here. Factor expression. Now it's not factoring. What's happening? Um, T is yeah, this is T here. Or maybe I should just keep it at X. Maybe I don't know if there's something special about that. So let me keep it at X and see if X works better than T. Interesting. That'll be so interesting. Okay. Is it that it's too long? Okay. Well, it's not that's not working, so I just leave it. I wonder why though. Maybe it's too much. Yeah, but this one is down here, so we are good. So you can also verify solutions, right? How do you know your solution is right? So if imagine if you solve this, your answer will be 3 and 2. Normally, if you substitute 3 or 2 here, you should get 0. And that's why you know your solution is right. So verifying solutions now, you have x equals sp dot symbols x, equation x squared minus 5x plus 6. So solutions, you have sp dot solution, solve this equation with respect to x. So for s in solutions now, you have two solutions for a quadratic expression. So if you now print equation dot subs, so substitute the value of s, each value of s, like 2 and 3 for x in the solution. If the two of them give you 0, then it means your solutions are correct, you know. So just like when you stop, so if you substitute 2 here, now this is 2 squared, that's 4. 4 minus 10, that's minus 6. Minus 6 plus 6, 0. If you put 3, 3 raised by 2 is 9, minus 15 plus 6. So 9 minus 15 is minus 6 plus 6, that's 0. So that tells you 3 and 2 are correct solutions. So you can verify your solutions like that. In conclusion, we see here that SymPy provides powerful symbolic mathematics capabilities in Python. So we learned how to solve algebraic equations, solve systems of equations, solve inequalities, solve nonlinear equations, work with matrices, perform numerical solutions, and solve differential equations. SymPy is widely used in scientific computing, engineering, physics, robotics, artificial intelligence, and mathematical research. So you can find these things very useful. So maybe you have an assignment. So having done it, you don't want to check if what you have done is correct. You can use this a lot. So we have some practice problems. Interestingly, this time around, the practice problems come with the solutions already. So that's rare, right? So we have 2x plus 7 equals 15. So you want to solve this. So of course, you import SymPy as SP. They declare your variable sp dot symbols x. Then solution sp dot solve 2x plus 7 minus 15. with respect to x, and that gives you the solution. So if you copy this into Jupyter Notebook or into a Python environment, you get your result. So here, of course, 2x is going to be 8 and x is going to be 4 in that case. So then for problem 2 now, 5x minus 19 equals 16. Of course, 5x is going to be 25 and x is 5. So this is the setup for that. Just copy this into Google Colab and or Jupyter Notebook or something, you get your result. Then for problem 3, you have x squared minus 9 equals 0. This is the setup for that. And you just copy, paste, run, you get it. Then problem 4, x squared minus 7x plus 12. Here you're solving. Of course, the answers will be 3 and 4 most likely, and you'll be fine. Then problem 5, x cubed minus 8 equals 0. So you're probably going to get something in exact form here, but I'm not sure until you try it out. Then if you want to you want to evaluate the results, you can use eval function, eval f. So of course, this is rational equation. So multiply through by x minus 1, blah, blah, and you get your result. So, but this is the setup. Just copy this paste sheet and you get your results. And then problem 7, square root of x plus 5 equals 4. So you do the kind of thing I did the other time. Square both sides, you have x plus 5 equals 16. 16 minus 5 is 9. So it means x is going to be 3. And that, 16 minus 5 is 9, right? 16 minus 5 is 9. So that means square both sides, that's x plus 5 equals 16. So 16 minus 5 is 11, sorry, 11. So 11 plus 5 is 16. Square root of 16 is 4. That's that. But this is how to go about it. Just copy paste. Then problem 8, you have sin x equals 1. So you solve trigonometric. You can also do solve sets to get all the possible, finite sets like that. Then problem 9, cos x equals 0. Same thing. You can use, after using SP solve, you can use solve sets to get the range of solutions in more general terms. Then this is quadratic. Of course, this is 2 raised to power 5. X is 5 for sure. But this is the setup to get that. Copy, paste, run. Then problem 11, log x is 3. So this is exponent. This is, take this to be natural log. So this is going to be exponent. E raised to power 3 is going to be your answer. Exponent of 3. Then problem 12, you have inequality, and the setup is you just copy paste and you get your result. This is a system of equations which can be easily solved. Add the two sides, you have 2x equals 4. And since 2x equals 8 rather, so x is 4. If x is 4, that means that y is 3. But this is the setup for it. Then problem 14, also done already. So system also, you solve and you get your result. Then 15, you have 3 variables here, x, y, z. So you can use matrix form. You can also use this solve thing. I demonstrated the matrix one too, so you want to check out anyone you want to use. Solve the nonlinear system. So here you have SP.solve again, taking care of that. All right, so just copy paste the codes and see how it works, and then you can tweak it to see what you get. You can also solve numerically. You have all of this when you solve numerically. This is out the setup for that also. And then you have problem 18, e raised by x is 4x. Things get a bit more complicated here, but of course, using nsolve, you get it in numerical forms, in numerically. Then problem 19, simplify x squared minus. Of course, we know this is going to be just x plus 1. This is one of the most common thing we've seen under this playlist. Then here you want to factor x squared minus 10x plus 25. So you have all of this. So with this, we come to the end of this interesting video. Interestingly, this time around, all the problems, the problem sets, each problem has its own solution. You just need to copy and paste the code and get going. Let me know how helpful this is for you. And if there's something else you'd like me to try out, feel very free to let me know. If you have subscribed to this channel already, I thank you very much for doing that. If you have not subscribed, why not go ahead and do that right away? After that, you can become a member of the channel by clicking on join. That comes with some special privileges, which you find out when you click on join. Ultimately, don't forget to comment, like, share, so that more people can have access to the great content I have going on here. Till I come your way again, keep doing math right. Bye.